Greetings and welcome to a new video about MOSFET differential amplifiers. This is our example number 5. In this example we will discuss a more advanced current source to feed our differential pair here. We will see that we have a Cascode current source, but now we have a full transistor configuration of it. This MOSFET MM7 here is the extra MOSFET we will add here to create this current source. Instead of a resistor here, we will see that we have a MOSFET here. And also we have again our RD here to create that load. We will see shortly the details for calculating the voltage gains for differential and common mode. Of course, we will see that shortly step by step in our calculations and also verify this in SPICE simulations. So this is our circuit. We see here again this M1 and M2 for our differential pair. And the Cascode is realized by this M3, M4, M5 and M6, and also the M7 here in addition for our full Cascode current source. For our N-channel enhancement type MOSFET, so all of the 7 MOSFETs are N-channel enhancement type. The parameters are shown here. You see also M1 and M2 are matched, M3 and M5 are matched, and M4, M6 and M7 are matched. The threshold voltage for all transistors is 0.4 volts. The K sub N prime, which is the smaller the K, is 50 milliamps per square volts for the M1 and M2. For the others, this is 0.05 milliamps per square volts. The channel length modulation is 0 for these 3 transistors, M4, M6 and M7, and for the others it is 0.0 volts inverted. Okay, what we have is the following. We use a tail current of 600 microamps. It's actually this. And there will be also a reference current from here, which has a value of 1 milliamp. And we will use a DC voltage source VDD of 2 volts and VSS of minus 2 volts. And RD here, this one and that one, will be 5 kilo ohms. Now we again calculate these 3 parameters here for our circuit, which are the differential mode voltage gain and the common mode voltage gain, both in balanced form, and also use these information to calculate the balanced common mode rejection ratio. So let's see what we can do. First, let's designate the current directions here. We have our IRF here already, but let's do that more explicit. And also this IX, which is our tail current. So this must be 1 milliamp, this must be 600 microamps. We know that in the DC operation, and this, since the circuit is symmetric, we have an IS1 and IS2, which will be exactly equal to half of this IX. So 0.5 times IX here and 0.5 times IX will be here at IS2. Since the gate currents are 0, that means that the drain current 1 and drain current 2 will be also equal to IS1, and this will be equal to IS2. Okay, let's look at our calculations in the solutions. First, drain currents, as said before, for M1 and M2 will be divided in equal parts, so it's split in 2 equal parts. So what you get is then the ID1 is equal to ID2 will be then tail current, which is ID5 or IX, over 2, that will give you here 300 microamps. We also know that the M1 and M2 are matched, that's actually given, and they are biased at the same potential. So the gate to source and also the gate to source for DC are exactly the same. And that will result in the transconductance of M1 and also the transconductance of M2 are exact same. So GM1 is equal to GM2. So we can calculate that and use that as a definition. We say then just GM. Now GM for M1 or M2, that's given by this expression, 2 times the square root of Kn1 times the ID1. This is again, remember, the DC drain current. We know the DC drain current, we know the Kn1 because that is related to that small letter K sub N prime, which is given by this. And here we need the ratio of the W over L. So that is given for the MOSFET 1, which has a multiplication factor here, which is 1. For example, for M7, it is 10. So we need to use here 1. Now, if we now substitute the values here, we know the Kn1 is here, so 50 milliamps per square volts. This is 1, so we get here then 25 milliamps per square volt. Then we can calculate the GM because we have now these values. That will be then 5.477 millisiemens. Okay. The first question is the balanced differential mode voltage gain. That is given by this expression, VOD over VID, so differential mode output voltage divided by the differential mode input voltage, which is then minus GM times the parallel combination we see at this node, which is the RD and the RO1 of this M1. And RO1 is due to that channel length modulation, so we can express this also like that. So due to the channel length modulation we have for M1, which is 0.01, the lambda. So we need to use this formula to calculate the RO1 also, but we don't know what VDS1 is. We can calculate it, of course, but we know also most of the time that the VDS1 is smaller, much smaller than the 1 over the lambda 1. So in general, we can then say, let's approximate this like that. So we just forget about the VDS1. We get this, and since this is 1 over 0.01 and the ID1 is 300 micro, we get here 333 kilo ohms. Okay, so we can now calculate that. We know the RD, we also know GM. Now we also have the RO1 here, and the parallel combination can be calculated here. You get here minus 26.98, almost minus 27 as our balanced differential mode gain. The balanced common mode voltage gain is given by this expression, which is for single-ended output, and that means actually the following, that you look at one of the outputs, so VO1 or VO2, that doesn't matter, divided by the common mode inputs. It's actually you connect the two gates together and you apply one signal here at the input. Now the RO here, the capital letter RO, is the impedance or resistance looking at the drain of M5. That's actually shown here graphically. And that is given by this expression. I don't drive this formula because that is, it will take some time, but it is quite straightforward if you use just Ohm's law. And you will have here this multiplication factor here in the second term, but you see also again this RO5 plus an additional term, which is then 1 plus the GM5 times RO5 times RO3. Okay, so we need this formula, and then we also then need this RO3 and also the RO5. So let's go first for RO3, which is again a similar formula as we have for RO1, but we know that VDS3 needs to be calculated, so we can skip that part because we know that VDS is again much smaller in most cases than 1 over the lambda, and that will give us now here 167 kilo ohms, similar for the as RO5 because they have the same drain current and also the same lambda. So we can just move on and calculate also this in a similar form, so we get also 167 kilo ohms. Now we have our formula, and we also need the GM5, which is the GM of this transistor. So how do we do that? Now you need to use the drain current of this transistor, which is an ID5 or IX, which is our tail current. We also need this KM5, so that means the KM5 is similar to KN1 and one half, so 0.5 times KN5 prime times W over L of the M5 times drain current of M5. Now W over L of M5 is here 148.81, so it is not 1, so approximately 149. So you just substitute here the values we have, so then you get here 50 micro because this is 0.05 milliamps per square volt, and you have your W over L ratio and also this 600 microamps for our tail current, which is IX. This is the same as IX, and this will give you 2.988 millisiemens, almost 3 millisiemens. Okay, now we have our necessary information to calculate this RO, because we know our RO5, we know the GM5, we know the RO3, and that will give us a pretty large value for our RO, which is then here 83.67 mega ohms. Now we already said that VO1 is our output where we measure, but VO2 will be the same because the both inputs are shorted together to one input signal. And that is now defined as the output common mode signal, which is then VOC. So this single-ended version will be then the balance also. There's no difference in the common mode gain formula. And now we see here the RO again, which is calculated. And we also know the GM here, which is from the beginning. So we can just substitute everything in here and you get now minus 2.94 times 10 to the power minus 5. So pretty small actually, so it's almost nothing. But that is not 0 exactly, so there is some number. So we will see what we need to do here, and also check this in the simulation shortly. Now let's bring everything here together and also do the common mode rejection ratio, the final part, which is the differential mode gain over the common mode gain, both in balanced format. We know the values, just calculate it, and it will give us 918 times 10 to the power 3, which is quite high, and in dBs it is 119.3 dB. Okay, let's bring now here the values we have calculated for A, B, and C. Now we go first to the DC part, which is first left side is differential mode, and this is common mode. What do you recognize? 1 milliamp, 600 microamps. So this is as we have as required. The similar form we see for the common mode circuit. We also see that the ID1 and ID2 are exactly the 50% of the 600 microamps tail current, which is also valid for the common mode. So we can say this is checked. Now going to the simulation result for the transient response. First we start with the differential mode. That is now the blue one is our differential mode input voltage, which is 10 millivolts peak with a 1 kilohertz frequency. And the red one is our differential mode output voltage. You see also that it's inverted, that's why we have this minus sign. And when you now do the peak value of the output signal divided by the peak value of the input signal, that's shown here, and that will give us minus 27.1, which is really close to the minus 26.98. So we can say this is also checked. Now going to the next check, which is our common mode gain. So the plot is here, and this is for the common mode operation. What you see is again the common mode input signal, which is our blue line, which is again 10 millivolts peak and 1 kilohertz signal. And what you see that the pink and the red one are the VO1 and VO2 respectively. So this is VO1, which is this one pink, and this is the VO2 signal, which is this red one. But they are in phase, but they are out of phase with this input signal, which is the blue one. That's why we have this minus sign here. And what you also see is that these values, there's almost 0.5, but in order to have the accurate measurement, you need to really make this precision higher. And what I did was take the maximum and the minimum value here, and then take a difference between those two. And that is calculated by the simulator, which is then 588.92 nanovolts. So pretty small, but that is really the peak value here. So what you get is this is the common mode input voltage, as I said before, and this is drain voltage of M1. It doesn't matter, you can also take the drain voltage of M2. But when you now do the common mode gain here, which is then as said 588.92 nanovolts peak, that's really from this cursor, and divided by the 20 millivolts peak, so that will give you really minus 2.94 times 10 to the power minus 5, which is exactly as we have calculated. So this is actually fantastic. So this is also checked. Alright guys, this is our example about the MOSFET differential amplifier, where we have used the Cascode current source realization without any transistor. So this is actually a full transistor configuration. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. In the next example, I will try to also use the active load for the same circuit and make the gain even higher. So stay tuned, and don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video.